Well, first of all, thank you very much for inviting me to this very exciting event. If my plug wants to open, yes. So, in order to frame my talk, I want to emphasize that I've tried to be a physicist and a hedge fund manager for the last 20 years. And so what I'm going to say is affected a lot by my own story, if you will. So CFM is actually a hedge fund. So what I'm interested about is why and how market prices move. And as you all know, the efficient theory, market theory, which is still underpinning most of the financial engineering industry, assumes that essentially prices reflect faithfully the fundamental value and we should trust markets. They should only move through exogenous, unpredictable news. So it's very much a Platonian view of markets that reveal fundamental prices without ever influencing them. Or maybe it's a mere tautology. So in this view, markets are fundamentally stable. Any mispricing is supposed to be arbitraged away from those who know. And again, after 20 years in the financial market, I really wonder who exactly is supposed to know. And my view is really very much what Fisher Black anticipated in his paper in '86, Noise, where he says that an efficient market is such that prices are correct within a factor of 2. And I think this is basically correct, and it explains a lot of what we're seeing. So of course, if you push efficient market to its end, you of course have to imagine that crashes can only be exogenous and never induced by market dynamics itself, really. Milton Friedman used to say that market stability was trivial and not even an interesting question, whereas I think that feedback loops and instabilities are everywhere. So what is important here is that when you're a financial mathematics student, you have to swallow this broth, and it has consequences. I want to quote here Van Hanke in September 2010, who said, "I think that calls for radical reworking of the field go too far. The financial crisis did not discredit the usefulness of economic research and analysis by any means." But then he carries on and says two things which I think is very important, at least for my talk today. He says, "The crisis should motivate economists to think further about their modeling of human behavior. Most economic researchers continue to work within a classical paradigm that assumes rational self-interested behavior and maximization of expected utility." And then he says another issue brought to the fore by the crisis is the need to understand the determinants of liquidity in financial markets. The notion that financial assets can be always sold at prices close to their fundamental value is built into most economic analysis. So I want to take on these 2 points. So my conviction, based on several things that I'm going to try to convince you of, mostly data and anecdotal evidence, is that we humans are lost in the dark. We really don't know what we're doing. We're swamped by super abundant information. There's radical uncertainty. We make mistakes all the time. We're subject to biases. And for me, in order to understand what's going on, we need to understand and include in models heuristic rules that I think we all follow to make suboptimal decisions. We're strongly influenced by the behavior of others. We always think that they might have more information than ourselves, so panic feeds panic. We're also strongly influenced by past patterns that we think might repeat, and trends feed trends. So for me, at least these 2 aspects should be a starting point to model human behavior. Theories that treat these effects consistently are still in an early stage, and I'm going to show you below one attempt to include herding in a model that is very suggestive, I think. So the other point raised by Van Hanke was liquidity and the impact of trading. And as an empirical fact, what you find, and I'll expand on that later, is trading, even with relatively small volumes, in usual market conditions, moves prices in a measurable way. And this is called price impact. And of course, it's very important because impact transforms trades into price changes. It's a way people think to include information into prices, but it's also maybe a way to destabilize markets. So understanding impact is fundamental to understand market dynamics and stability. So about impact, there are again two stories here. One is the efficient market story, which says, well, no wonder trades impact prices. It's because informed agents forecast future price changes, and they're right. So they think the price is going to go up, they buy, and price goes up. But if you're uninformed, you shouldn't affect prices, because otherwise prices will err away from the fundamental values. The story that comes out of a lot of empirical study is that actually there's no way for the market to distinguish informed and non-informed traders. So all trades, on average, do statistically impact prices. And actually we've done the experiment. We've launched random trades in the market and found that their impact is the same as any other trade. So why? Well, agents believe, as I said, or fear that trades might contain useful information they don't have. So they react to that in anticipation. But it also means that silly or random trades impact prices, and this is a transmission belt for feedback loops and avalanches. So some questions with empirical answers. What's great about financial markets is that they offer terabytes of information daily. And we can try to use them to investigate why and how prices move. This is important for financial engineering, of course, as a whole, and trying to make better models that don't run into problems that we've all witnessed in the past few years. But I think it's also important from more general questions, like macro questions, because finance is an ideal test bed. Some of these fundamental questions that we will ask ourselves. So, for example, market stability. So, first point, is market dynamics mostly exogenous or endogenous? Point B, how do trades impact prices? So here I don't have time to go into the details, so let me flash a few bullet points here. There's been an accumulating body of observations. Jump sizes, prices jump all the time, and the distribution of these jump sizes is powerful, which means that there are crises on all scales. It's like earthquakes. There are big crises and small crises. And what's interesting is that the distribution of price changes is very much universal. It doesn't depend on the asset that you look at. So for example, here I show the daily changes of the implied volatility on option markets, which is a very abstract thing. But it's traded, and because it's traded, it generates these parallel tails, which are exactly the same as any other financial asset. Second thing, most jumps appear to be unrelated to any news at all. They look endogenous. They look to be generated by market dynamics. I would like to have time to explain more details, but I don't think I will. So maybe the questions. And then last, if you look at the volatility in all markets, what you find is a pattern like this. So for example, this is one of the ways to exhibit this intermittency. It's the number of weekly 1% jump per minute on S&P stocks from the mid-90s to now. And what you see is that the market has this funny way of being agitated and then calm for a while and agitated again. So there's excess volatility. This has been pointed out by Katharina, and well known, but volatility is also very long-ranged in memory. And as a physicist, it's strikingly similar to other systems that are called complex systems, where you also see this very intermittent dynamics, although the system is driven by a very continuous and featureless exogenous drive. The complexity comes from the system itself. So this is called Barkhausen noise. It's the way the magnet screams when you try to polarize it. And this is a turbulent flow, so I won't explain in details, but I think what is striking is the analogy in phenomenology. So, to a large extent, as I said, these are universal observations. In time, you can make a study of a century of Dow Jones Index, and you find that what's remarkable is not how much it's changed since the beginning of the 20th century, it's how much it's stayed the same since the 1900s. So in time, space, and assets, details may evolve, but main features remain. So for me, this really suggests that endogenous dynamics is fundamental, is determinant to, and explains, for example, it says volatility puzzle. Volatility is not due to fundamentals, it's due to trading, which is allowed, and remember the story of Fisher-Black. If prices are allowed to vary by a factor of 2, there's quite a bit of room to move around. So actually you can be a little more precise in that, calibrate models to try to distinguish the part of the volatility that's exogenous and the part that's endogenous. And all these models, when you try to calibrate them, they give at least 80% of volatility due to self-reflected feedback, which is huge. So we really need models for endogenous prices and discontinuities. So second empirical point, how do trades impact prices? And here, as a trader, as I said, what you realize when you're wanting to trade in markets is there's a fundamental paradox, which I call the paradox of liquid markets. Even the most liquid markets of the planet are actually very illiquid when you look at them instantaneously. That is, if you want to trade 1% of the daily liquidity of a big stock, you can't do it right away. You have to, your order is 50 times too large compared to what's available right now. So you have to cut your trade into pieces and execute incrementally. So that's what we call a meta order. A meta order is the family of all the trades that's related to a single operation that you want to make. So to summarize, the traded daily volume is 5,000 times larger. That's what's available instantaneously in the order book of a very liquid market. So a very liquid market is very illiquid. And as I'm going to try to show you, this has an interesting consequence, which is that if you try to measure the average impact of a meta order of size Q, then what one finds empirically, and I'll go through very quickly on that, you find a very funny law, which is extremely robust, that holds for many different strategies, markets, tick sizes, whether you execute limit orders of market orders, periods, whether it's mid-90s or now, different groups, everybody concurs to say that the impact of meta order of size Q is proportional to the volatility of the underlying times the square root of the volume you want to trade divided by the daily volume of the market. So that's our data. We have a lot of trades, so this is average of 500,000 trades, so pretty good statistics. And this is amazing, because what's amazing is first of all that it's so universal, but also that it's non-additive. So 1 plus 1 is not equal to 2. If you trade 1 and then trade 1 later, your impact doesn't double, it's compared. But also, if you remember what's a square root is singular at the origin. So it also means that there's anomalously large impact of small trades. And if you work out the numbers, you find that trading 1% of the average daily volume pushes the price by 10% of its volatility, which is huge. So being small doesn't mean that you don't impact markets. You actually impact markets a lot. So why is impact so large and liquidity so small? So we've thought about this for 5 years because we have this data for a long time, and the fact that it's so unusual suggested that it was something interesting to understand. So we came up with a kind of statistical theory of liquidity which assumes as little as possible. Essentially that, if you have zero intelligence agents which do random trades, then the only assumption is that if the price makes a random walk, which empirically is well established and is related to impossibility of making money too easily if you want, then what you find is that the probability to have unexecuted orders close to the current price is linearly small. And this is a very generic result. So it means that close to the current price, it's a minimum available liquidity, which is paradoxical but interesting. And so it means that as soon as you want to trade, you're going to be big compared to something that's small. So of course, again, I refer you to the papers, and I think Doan will speak a little bit about this later. But you can come up with both an analytical theory based on the diffusion equation to show that the liquidity pattern is like this. So here is the current price, and this is the volume available. And you see that it's zero around the current price and then builds up. But we've also made agent-based models to confirm that. So if you think a little bit, you realize that the fact that the supply curve is linear immediately implies that the impact is a square root of traded volume. And the intuition is that as price moves up, more and more sellers opposing you will show up because you're moving up this curve. And so your impact later in the day will be reduced compared to the impact right away. So what it means is that liquidity is small, so markets are intrinsically fragile. So I think that markets are not by no means obviously stable. If liquidity is small, then liquidity fluctuations are bound to play a crucial role. And I think this is intimately at the origin of these micro crises and jumps without news that we see all the time. Of course, it would be important to go down that line and understand quantitatively how to describe these return distributions based on this mechanism, but I'm kind of convinced that this is a promising avenue. Okay, well, of course, regulation should engineer stabilizing feedback loops to favor liquidity when it's most needed, and this is related to the current debate around high-frequency trading, but I don't want to touch on that. So what I want to move on to is how to build models that include what I said earlier are important items, that is, people imitate each other and people tend to follow past patterns. So I think that there's a lot of direct empirical evidence that people do not make decisions in isolation, but rely on the choice or opinion of others. I don't have time to review that evidence, but there are very interesting recent papers showing that in kind of well-controlled experiments. And of course, we see all the time these strong distortion amplification phenomena due to imitation, like fads and fashion, bubbles and crashes, which would be very difficult to understand without imitation. So let me show you what happened in Paris in the last 3 or 4 years. This madness of love locks. So people put the love lock on Paris bridges, and there are tens of thousands of these locks now. I mean, it's just crazy. And it popped out of nowhere, and people walk and they realize that other people are doing this, and they want to do the same and write their names and so on. So really, the madness of crowds is what we need to understand, as Newton was saying. It's of course very important for many situations in practice, like vaccines, hygiene campaigns, fertility, driving, crime, tax evasions, technology adoption, and so on. So in physics, there's a very interesting model that I'm going to call a cartoon model, because it's just a unifying framework for many phenomena that has been invented to explain this Barkhausen noise that I've shown you earlier. And if you want to read about it, there's a beautiful review paper by Svetna et al. In 2001 called Cracking Noise in Nature. And we've ourselves used it to understand several empirical data, like birth rate collapse in Europe since the mid-60s, the way cell phones invaded the market in the late 90s, and as I'm going to show, how clapping ends at the end of concerts. So imagine that you have n heterogeneous agents, all different, but influenced by the behavior of others. And these people, they have to make a binary decision. So I'm going to call the decision plus or minus 1. And of course, what's interesting in this model is that it can be adopted to many situations, like to buy or to sell, to lend or not to lend, to trust or not to trust, to be optimistic or pessimistic, and so on. And I'm going to call the aggregate demand the average over all ends of their decision. So in the context of physics, there's various factors influencing this spin, as it's called. And if I translate it into economics or finance, let's imagine that every agent has 3 influence factors. It's personal opinion or propensity or utility to do the thing. And we're going to assume that this is heterogeneous with some probability p, and this probability p has some width sigma. It doesn't have to be detailed what kind of distribution it is, but think about it as a Gaussian, but it doesn't really matter. It just matters what its width is, sigma. Second, there's public information about thing to do. So if you think about buying a cell phone, it might be the price of the cell phone, might be technology level. At the beginning, the voices were all garbled, and it was not very nice to have a cell phone. Now it's much better, so people are more interested, and so on. Can be news, can be just zeitgeist. So I'm going to call that f of t. And for illustration purposes, let's assume that this external news is smooth in time. There's no accident. So, for example, the price doesn't jump down suddenly. It's just a continuous evolution. And last but not least, in the decision process, there's social pressure or imitation effects. So each agent looks around and has a number of agents, J, and makes a polling of the opinion of others, and this is included in what he's going to do. And this random field icing model update rule, as it's called, says that your decision at time t is the sign of the sum of these three influence factors. Your propensity, the external news, and then what your neighbors are doing. And I'm going to discuss here a simpler case, which is generic as well, which is the case where people are influenced by the aggregates only. So, for example, there's a polling done, or people know how much cell phones have been sold and so on. So in this case, JIJs are equal for all pairs and equal to beta over n. So beta is the imitation strength. So what goes on in that model? Well, it is interesting because there's a transition between two possibilities. As time evolves and, say, bad news accumulates slowly, so maybe this is a cartoon of what occurred in 2008. And what I'm drawing here in the y-axis is the fraction of pessimists, people who think that is really going to go all right. So as a function of time, nothing really changes. And there's a slow evolution of people realizing that banks are maybe over-leveraged and so on. And depending on whether this imitation parameter is small or large, you can have either a kind of soft landing, where progressively people change their mind and this fraction evolves smoothly in time. But as soon as this imitation parameter exceeds a well-defined threshold, then the curve becomes discontinuous. And nobody believes any of the pessimistic news because everybody else is continuing dancing, and then suddenly there's a final crash, which is sudden. So it's a very interesting model because, first of all, it's a model where you have explicit breakdown of the representative agent, and you get spontaneous discontinuities even if the outside world is continuous. So that's what I said. If imitation is weak enough, personal choices dominate, and there's a smooth demand curve. But when beta exceeds some threshold, then hiding dominates, and there's a huge distortion of the fundamental demand curve. Discontinuities appear at the macro level. What's interesting too, actually, is that in that phase, we're on the way down, so to say. So if news got better, then there's hysteresis. That is, you have to wait a long time before people get convinced to go back down to being optimistic. What's interesting too is that the model actually tells you a lot about what happens around this critical point. The dynamics is avalanche-like, power distribution of sizes. And what's also interesting and relates to Katarina's point earlier on is that this imitation strength is proportional to the dispersion of the opinions. So more dispersed opinions avoid polarization and stabilize the system. So that's what happens in clapping. If you record clapping at the end of concerts, then people can be either indifferent to what other people think if they start clapping, if they continue clapping all by themselves, or like in France where people are very attached to the etiquette and would not be very happy to wear caught off guard. So here you see a clapping that goes down continuously, and in other cases you find that clapping ceases abruptly. Of course, this is anecdotal, but you can extract positive results from these experiments that are explained by this random theorizing model. There are other examples of application of this idea. So for example, this is a model of evaporation of trust, which I personally believe is crucial to understand the crisis. If you look at the black line is a kind of average trust that people give to the whole system, and as they trust more, they connect more to other counterparties, but they also become more vulnerable to the default of one of them. And what you see as a function of time, in this model, nothing happens. It's just, by accident, one company defaults and triggers an avalanche of defaults around it. And so you see these big trust crises, which are due to the fact that I trust you because he trusts you because I trust you. So as trust builds up, the system becomes more fragile. And this kind of model has been developed also by the Battiston group and Alan Kerman and so on. So in conclusion, endogenous crisis, I really believe that financial markets, the economy, and many other social phenomena exhibit crisis, ruptures, sudden discontinuities that resemble far from equilibrium phenomena in complex systems.